Assalamu alaikum warahmatullah. Today is our class to continue the parallel programming models. As you remember, last week we have gone through the shared memory model and the trades model, and we stopped here on the trades model on slide 21. So here, actually, we have something called OpenMP. So OpenMP actually is an implementation of what they call it parallel or threads model. So OpenMP, okay, OpenMP is here. This is the main website for this. The OpenMP, as I mentioned earlier, it's an implementation of the trades model. And this implementation actually, or this project is an open source project and free to download, free to modify, and so on. So this framework actually is based on C and C++. So as you can see here, the OpenMP API supports multi-platform shared memory parallel programming in C and C++. And for Tran, the OpenMP API defines a portable, scalable model with a simple and flexible interface for developing parallel applications on platforms from the desktop to the supercomputer. So this library actually is to help the programmers create or design their parallel applications or parallel programs to run huge tasks that requires concurrency. Okay, so again, here OpenMP is a compiler directive based that can use serial code jointly defined and endorsed by a group of major computer hardware and software vendors. So this library actually is very common, and you see it's endorsed by a group of major computer hardware and software vendors. So it's well known. Many vendors are compatible with it. Many vendors use it for their platforms or for their supercomputers to perform a huge tasks based on parallel programs. Okay, so OpenMP is a Fortran API which was released in October 28, 1997. So at the beginning, it started only as a Fortran API, but after a while, after about 1 year, they also released the API of the C and C++ in 1998. So portable and multi-platform, including Unix and Windows NT platforms. So it can work over Unix and Windows, and also over Linux. Available in C, C++, and Fortran implementations. So this is the implementations that are available. I'm not sure whether today Fortran is still available or not. But maybe we can try to download, because this one really OpenMP download. Okay, let us see here how many versions they still have. Okay, they still maintain the Fortran, and now is the version 11.1, and the Fortran, the latest compiler actually is Fortran 95, which reflects the year of the establishment actually. So this one was released in 1995 and until now still in use. And also they have one package for the AMD using C and C++, and also package for the ARM architecture, which is also using C, C++, Fortran. It's available on Linux only. And here for supercomputing center, this one is for classic Flang. Fortran, this one is Fujitsu, GNU, IBM, Intel. So you can find whatever you need. If, for example, you have an NVIDIA-based parallel computer, so you can use this one, this package. By the way, in our faculty, we have many computers in the parallel and distributed computing lab in the ground floor, block C. So there we have many computers that has multiple processors and also multiple GPUs based on NVIDIA and other brands. Okay, so if you are interested, you can later, if for example you want to make something for your final year project as or under parallel and distributed computing, you can go through these packages, and you can go to the lab and try some ideas there, maybe based on whatever you want to implement for your final year project. Okay. Then what else do we have here? Actually, it can be very easy and simple to use, provides for incremental parallelism. So this library actually makes the life of the programmer more easier. Okay, because the programmer doesn't need to handle all stuff for managing the resources, for managing the memory, for managing the processing units, for managing locks, for managing synchronization. Does not require to do all of that stuff, because this framework could help. It can achieve a lot of that tasks automatically. Okay, so here on the right side, Microsoft has its own copy or its own implementation for threads, which is not related to the Unix POSIX standard or OpenMP. So here, as you can see, we have a standard for Unix, as we mentioned last week, which is called POSIX, and also we have the other standard, which is the one that we currently talking about, the OpenMP, and also Microsoft, they have their own implementation. Okay, the message passing model. So here, this is a new model for parallel programming. So message passing model demonstrates the following characteristics. So a set of tasks that use their own local memory during computation. So each task here, we have list of tasks or set of tasks running concurrently, and each task has its own local memory during the computation. So multiple tasks can reside on the same physical machine. So these multiple tasks could be run or could run over the same physical machine. So as well across an arbitrary number of machines. So it can be reside on the same physical machine, or could be reside over a number of machines that are connected through, for example, a cluster or whatever. Okay, so tasks exchange data through communications by sending and receiving messages. So if when we have multiple tasks running over multiple processors on the same machine or on different machines, so those tasks can communicate only by exchanging messages. So every task, when it needs something from another task, it will send message, then the other task should be ready waiting for it. And when it's the other task received the message, it should reply by the needed data. So it should find the needed data and send it back to the original task. Okay, so that data will allow the original task to achieve its own job, okay, or its own task. So data transfer usually require cooperative operations to be performed by each process. So when we say data transfer or message passing, so that means we have sender and receiver. So in order to get this kind of communication happen, we have to do a kind of cooperation or kind of cooperative work to support that message passing. So for example, a send operation must have a matching receive operation. So when one task sends data, there should be another task that's waiting for this message to take it or to receive it and handle it. Otherwise, if we miss this kind of cooperative operations, then the system will not be able to work. Okay? Is there any question, guys, so far?
So far, no, Doctor.
Okay. Okay, here we have something called message passing model implementations. So this one, in this slide here, we will talk about the implementation of a message passing model. So this message passing model implementation, they call it MPI. So MPI is a very common thing, which is also available. MPI is a library also, or API or a framework that's available. It's free, open source, available for everyone to download, to modify, and so on. And also, it's compatible with many vendors, many hardware, many architectures. Okay. Here, for programming perspective, message passing implementations commonly comprise a library of subroutines that are embedded in source code. So here in the source code of the MPI, as I said, is a combination, is a library or API. So that library has a lot of subroutines or sub-libraries inside it, embedded in its source code. So the programmer is responsible for determining all parallelism. So the programmer here, as I mentioned earlier, the programmer here is responsible to do the determine all parallelism or all tasks that need to be run in parallel mode. In historically, a variety of message passing libraries have been available since the 1980s. So the concept or the idea is not new. It started in 1980s. So these implementations differed substantially from each other, making it difficult for programmers to develop portable applications. So the problem actually, when they started the 1980, at that time, every vendor or every company, based on its own standard, they built their own library or their own API. So their own API for the message passing model. So that's why when a programmer create a software or a program for a certain vendor, so that program cannot be run over another vendor. Why? Because the other vendor have their own different library. Okay, and if we want, for example, to take the library X prepared by a certain vendor and we want to run that X library over another vendor machine, it will not work. Why? Because they suffer a lot of compatibility issues because they have different standards of hardware, different standard of architecture, different standard of operating systems, and so on. So here in 1992, the MPI forum was formed with the primary goal of establishing a standard interface for message passing implementations. So in the 1992, they realized that there is a problem because Programmers could build some softwares or some programs to run over a vendor, some machine based on a certain vendor. Then after a while, when they try to run it on different vendor machine, it doesn't work. So they realize that there's some issues that have to be solved. That's why they formed the MBI forum in 1992 with the primary goal of establishing a standard interface for message passing implementation. So they decide to make one standard implementation for message passing model library. So that library could run over any operating system, could run over any standard machine from any vendor, and so on. So here they started to go towards unification. Okay, so here after this formation of the MBI forum in the 1992, they produced part one, which is of the message passing interface. Part one of the message passing interface MBI was released in 1994. And the part 2 MBI2 was released in 1996. So you see this, the history of the MBI is very old. Actually, it's a new thing. It's not a new thing, not a new idea. And here, both MBI specifications are available on the web at this link. So here, if we want to go here, open hyperlink. Okay, let us go through this website and see what they have. I don't know why it doesn't open. Copy and paste, much better. So here, as you can see, this is the website that's related to the MBI, but unfortunately, that page was quite maybe old, or I don't know what happened, but in the last year it was running this link. So maybe you need to go through this website and try to find the MBI here. So maybe use search MBI. Library doesn't show anything, or oh, still need to. Okay. MBI tutorial to be held. Okay, let us go to, oh, sorry. Let us go to this, the first one. And we see here. So MBI tutorial to be held at Argonne on June 21. So the keys to blah, 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 MBI, where is it? It looks like they don't provide anything anymore. So maybe we need to go and find the MBI library download like this. Oh, sorry. So here, as you can see, there is you will find a lot of implementations actually. So as you can see here, there's something called Intel MBI library. So this one is designed for Intel processors. So if you want to run something based on Intel processors, maybe this package is okay. This package is proper. Then we have here version Windows binary installer. Here we can see something called OpenMBI. So this one OpenMBI is not OpenMP. because OpenMP is the one that we explained just before this. As you can see here, download Microsoft MPI, official Microsoft, and here we have MPI CH. This is another implementation. Here we have OSS software. We can download from here also, maybe different library. So you can find a lot of implementations for the MPI. And also here, as you can see, we have something called Python MPI. So depends on what you want to do, depends on what kind of hardware you want to use, and also what kind of operating system. You have to select the proper package. You have to select the proper library. Okay. So here in this slide we have the message passing model implementations in MPI, and we have some visual example here. So we will go through later. So MPI is now the de facto industry standard. De facto means the commonly used. The commonly used. So the MPI is well known, widely used in the computing environment. That's why they call it the de facto industry standard for message passing, replacing virtually all other message passing implementations used for production work. So in the production, you will find mostly the people are using MPI. Okay. Most, if not all, of the popular parallel computing platforms offer at least one implementation of MPI. A few offer a full implementation of MPI 2. So from this point here, we should understand that the parallel computing platforms providers, they can support multiple implementations of the MPI. They can support. They can offer that at least one implementation of the MPI. Okay, so for shared memory architectures, MPI implementations usually does not use a network for task communications. Instead, they use shared memory or memory copies for performance reasons. So the MPI here, it could be used for message passing and also based on shared memory architecture. So it could be message passing based on shared memory architecture. Okay, so in this case, the MPI implementation will not use network to for task communication. So the messages will not be transferred or exchanged over the network. It will be exchanged over the memory. Why? Because they need to improve the performance. Okay. One of the examples of running parallel programs or parallel tasks. So if let's say you have one array, and that array you need to apply some calculations based on that array. So maybe, for example, the first task need to do something based on columns, for example, from 1 to 25 to calculate this equation. And the other task is working over the columns 26 to 50 to calculate the same thing, but on different range of columns maybe, or range of cells. And also the task n could be from m to n. So in this way, maybe what we need to do is to divide the application, or to break down our application or program into subroutines or subtasks based on chunks of data. So what we need to do at first, we need to take the data, we divide it based on some variables, or based on some what they call it, based on some criteria. Then after that, we calculate or compute each chunk of data in a separated task to increase the speed and also to reduce the processing time. Okay. Then here we have in this slide. In this slide, we have we talk about the data parallel model. So data parallel model is different model. So at first, we to recap or to keep you with me. So here, what we have shared memory at first. Then after that, we have threads model. Then we came to the message passing model, and now we go to the data parallel model. Okay. So here in the data parallel model, where is it? Here. The data parallel model demonstrates the following characteristics. Most of the parallel work focuses on performing operations on a data set. So this is the key of using this model. So here, each task needs to perform some operations on some data. So the data set is typically organized into a common structure, such as an array or cube. So data could be an array, data could be a table, could be a cube, could be whatever, could be a file, whatever. Okay, each file or each chunk of data should be computed or should be performed by a task to apply or to perform some operations to compute or to analyze or to calculate something from that data. Okay, a set of tasks work collaboratively on the same data structure. So for example, if the data structure is array, for example, and for example, we have a set of tasks, for example, 10 or 20 or whatever, they need to work collaboratively on the same array. However, each task works on a different partition of the same data structure. So as you can see here in the previous example, these three tasks are working on the array, right? But each task works on different part or different partition of the data. Here from 1 to 25, here from 25 to 50, from 26 to 50, and so on. Then tasks perform the same operation on their partition of work. So for example, add 4 to every array element. So if let's say we want to add a value of 4 to every array element or to every array item, so in this case, the first task here maybe need to add 4 to the item of the array from 1 to 25, and this task will add 4 to items from 26 to 50, and so on. So all tasks here in this case will operate the same operation. Will operate the same operation, which is adding the value of 4 to the item or to the element. Okay, but each of the tasks run over different data, run over different columns or different cells of the array. Okay, guys, is that clear?
Yes, doctor.
Okay. On shared memory architecture, all tasks may have access to the data structure through global memory. So all tasks, as in this example here, actually this one is different model, but we still can use the same example. So in this case, we have n tasks, and all that n tasks can read the array. All of them can read the array. But if you can see here, all tasks may have access to the data structure through global memory. On distributed memory, so if the architecture is distributed memory architecture, the data structure is split up and resides as a chunks in the local memory of each task. So here this array, if we use distributed memory architecture, so this array will be divided into small chunks of data based on this n. So it will be divided to n chunks, and every chunk will be reside in the task local memory. Okay, so the task will be only able to access that chunk. Okay. Okay, let's go through the some historic information about the data parallel model implementations. So programming with the data parallel model is usually accomplished by writing a program with data parallel constructions. So what does it mean? Here, to make something called data parallel model, usually need to write a program. Sorry, guys. Usually need to write a program with data parallel constructs. So data parallel constructs like arrays or whatever. The construct can be a call to a data parallel subroutine library or a compiler directives recognized by a data parallel compiler. Okay, I know this is a theoretical part. It's a little bit confusing if you want to understand it without understanding the main concept. So later we will come to this point when we enter some or when we come to some examples, some practical examples. You will understand what's the meaning of that. So Fortran 90 and 95, or as it's shortened as F90 and F95, ISO and ANSI standard extensions to Fortran 77. So Fortran 77 is the Fortran, I think, released in year 77, and Fortran 90 is released in 1990, and so on. This is the style of Fortran. I remember during my bachelor time, we studied the Fortran 77. Then here contains this 90, Fortran 90 and 95 contains everything that is in Fortran 77. So it's only an extension. The 90 and 95 are extensions to the 77. So a new source code format additions to character set. It includes this new source code format. And also additions to program structure and commands. Also, it has variable additions, methods and arguments. It has also pointers and dynamic memory allocation added, and also array processing added, recursive and new intrinsic functions added. Also, it has many other new features. So all of these actually features added in the 90 and 95 Fortran. Okay. Implementations are available for most common parallel platforms. So implementations of this Fortran or these packages of data parallel model from Fortran is available for multiple operating systems. Okay, data parallel model implementations. We have one of the implementations, namely high performance Fortran HPF, is also available, which is extensions to Fortran 90 to support data parallel programming. It also contains everything in Fortran 90. It includes also directives to tell compiler how to distribute data added, assertions that can improve optimization of generated code also added, data parallel constructs added, now part of Fortran 95. So here is the new features added on top of the Fortran 90, which is called here high performance Fortran. Then here we have compiler directives. It allows the programmer to specify the distribution and alignment of data. So Fortran implementations are available for most common parallel platforms. Distributed memory implementations of this model usually have the compiler convert the program into standard code with calls to a message passing library, MPI usually, to distribute the data to all processes. All messages or all message passing is done invisibly to the program. So because of this library, actually the compiler directives, there are many things will be done automatically by this library without the without the interaction of the program. So the program doesn't need to take care about message passing, or doesn't need to take care about what they call it, the conversion of the program into standard code and so on. So it will achieve a lot of tasks automatically. Then at the end here we have other models. Okay, before we go to the other models, let us go and try to see what they call it, high performance Fortran. Download. So as you can see here, we have been taken to the same website anl.gov that we opened previously with the other implementation of the MPI. So here, as you can see, they have a definition for the Fortran, high performance Fortran, and also we can see here, somebody is asking in the Stack Overflow, is there a free high performance Fortran compiler for blah, blah, blah. So they maybe answer that question here. Okay, unfortunately this is not available. Oh, available, but what is that? There are no public domain high performance compiler, but there are several these alternative results. Okay, there are some implementations for that, for the high performance Fortran. So this one, an introduction. Computing for, I don't know. I think we have to go to the official websites to find that package, Intel Fortran compiler. So get it now here, and yeah, we can, for example, we can download it from here, from the Intel website. Anyway, you have, if you are interested in that, you have to carefully search, and you have to find the official copies of the libraries. Okay, no matter what kind of model you want to use, but you have to find always the official libraries to avoid any phishing works or any malicious code installed over your machine. Okay, the other models here, other parallel programming models besides those previously mentioned certainly exist and will continue to evolve along with the ever-changing world of computer hardware and software. So only three of the more common ones are mentioned here. First one is the hybrid, second is SBMD, which is single program multiple data, then multiple program multiple data model. Okay, this is the hybrid. Actually, we have gone through this before, but here in this slide is talking about it from different angle of view. So hybrid here, in this model, any two or more parallel programming models are combined. So any two models are combined to form the hybrid architecture or hybrid model, sorry. So currently, a common example of hybrid model is the combination of this one, MPI, with the threads model, which called POSIX threads. So this model is hybrid, which combines the MPI and the threads model. And also there is the OpenMP, which combines also the message passing model with the shared memory model. Okay? So it depends on what kind of models, what kind of architecture you want to use. So you can select what kind of libraries or what kind of framework you want to find, or do you want to make your program based on. So this hybrid model lends itself well to the increasingly common hardware environment of networked SMB machines. So SMB, what does it mean? SMB means symmetric multiprocessor. Okay, as we have taken in the previous slides here, if you remember. So where is it? Here, SMB, symmetric multiprocessor machine. Okay, so here, slide 29. This hybrid model lends itself well to the increasingly common hardware environment of networked SMB machines. So these hybrid solutions or libraries or models actually working based on the networked machines. So another common example of hybrid model is combining data parallel with message passing. So as mentioned in the data parallel model section previously, data parallel implementation is Fortran 90 and high performance Fortran on distributed memory architecture actually use message passing to transmit data between tasks transparently to the program. So this kind of hybrid model is also, as we have seen in the Fortran 90 and high performance Fortran, which combines the data parallel model and the distributed memory architecture. Okay, then we go to the single program multiple data, SBMD. So here we have only one single program and multiple data. Then SBMD is actually a high-level programming model that can be built upon any combination of the previously mentioned parallel programming models. So the combination of any parallel programming models, it could form the SBMD. Then here a single program is executed by all tasks simultaneously. So the same program will be run in different tasks, maybe in different threads. Okay, So that program actually will be responsible for a certain data, exactly similar to the scenario here. So this program actually here, the program is this line actually, AI equals BI times delta. Exactly the same, right? But the range of data is different here. So for this program, we give columns maybe or cells from 1 to 25, and for here, for this copy of the program, we give the data from 26 to 50, and so on. So that's why they call it single program, which means the same program runs multiple times, but every copy of the program manipulates or deals with different range of data. At any moment in time, tasks can be executing the same or different instructions within the same program, exactly as I explained. So SBMD programs usually have the necessary logic programmed into them to allow different tasks to branch or conditionally execute only those parts of the program they are designed to execute. So that is, tasks don't necessarily have to execute the entire program, perhaps only a portion of it. So the program actually could be designed in a certain way to decide based on the type of data or the range of data what part of the program it need to be run. Okay, so again back to this program. So maybe the entire program actually we copied different times and we assigned that copy of the programs to multiple tasks, but based on the data, maybe that program will decide what kind or what part of that program need to be run. So maybe for task 1 we run this code, maybe for task 2 we run different code using the same program. Especially if, let's say, we tested the data, maybe we use the if condition statement, and we say if data is greater than this, we run subroutine X. If data is less than that, we run subroutine Y, for example. So the code running is depends on the data assigned to the task. Okay, but in general the program is the same. The program is copied, so that's why they call it single program but multiple data. So all tasks may use different data. Okay, this will no. Okay, the last one is the multiple program, multiple data. Actually, this is the last slide. So multiple program, multiple data, from its name, it means we have multiple programs and also multiple data. So like SBMD, MBMD is actually a high-level programming model that can be built upon any combination of the previously mentioned parallel programming models. Okay, so it's also a high-level programming model. In the MBMD, applications typically have multiple executable object files or programs. So here we have multiple programs. While the application is being run in parallel, each task can be executing the same or different program as other tasks. So for example, in this case, let me also draw the previous case. So in the single program, multiple data here, they have only one program. So I will make it easy for you. I will mention the program. I will name the program like XEXE. So this is an executable file. The name is X. The extension is .exe. So here, that .exe is a executable program that could be run to achieve something or to, for example, brug.exe. Okay, so here in the SBMD, what they have to do, they have to take a copy of the same program here, Control Z, sorry. They will create multiple copies of the same program like that. For example, they have like 3 tasks, for example. Then suppose they have an array like this. So that program actually is the same, exactly the same copy of the brug.exe. So maybe here what they need to do is to take this chunk of data, they give it here, and the other chunk is here, they give it to this copy of the program, and this chunk of data will be given to this program. And maybe after that, after we calculate all of that stuff, so if let's say the program is to add 4 to each element, in this case we don't need to have what they call it coordinator thread to coordinate between them. But if let's say they calculate the summation of the items and they save it here, suppose that every program saves the average or maybe the summation of items. So maybe the first program result is 150, then maybe the second one result is like that, sum is equal to 200, and then the third copy of the program, the summation is equal to 57, for example. So here, after they finish, we have to have a coordinating or controlling task or thread to take the results, all of that results, this tree, to combine them together, and then to give us the final result, which will be 407. The summation will be 407. Sum equals to 407. So 407 actually is the combination of the 3 numbers. Okay, so here this calculation or this calculated summation need to be calculated by another program, maybe, which is maybe called a controlling thread, maybe, or a coordinating program or whatever. Okay, so it depends on the style of the program and the task done based on the code written. Okay, for the other thing, for the other model, actually, here, instead of this, what we have multiple programs and multiple data, right? So in this case, we don't have one program, but we have different programs. So maybe I will add something here in front. So maybe this one, a program. Okay, a program. Then this one is B program, and this one is C program. So each program here has different code, different commands, different functionality. Okay, so maybe that programs actually designed to be run on different data like this, maybe different chunks of array, or maybe different, what they call it, sorry, I need to control Z. Maybe on different chunks of the array, or maybe on different types of data at all different I mean totally different. So here maybe that data is triangle, this one is rectangle, or maybe this one is circle. Okay, so for example, this program number one, or A program, and this one is B program, and this one is C program. So maybe program A is designed to calculate the maybe the size of, or maybe it calculates the what they call it, the La ilaha illallah. I lost my words, guys. Sorry for that. So I received many calls, then I lost my focus. So maybe program number A actually is designed to calculate the area of the shape, rectangle shape, and program B is designed to calculate the area of triangle shape, and program C is designed designed to calculate the area of a circle. So in this case, we have different programs, different data, right? So far, is it clear, guys, or not?
Yes, Doctor. Clear.
Do you need any other clarification? Maybe I use different examples, or maybe
No, it's okay.
clear. Okay, good. Okay, that's all about the programming models. So I think we finished this for now. And let us go through the until now. So far, we finished the chapter 1, chapter 2, and chapter 3. And now we still have chapter 4, which is all about the analysis and scalability. And after that, we have the designing of parallel programs. We also have some examples here, parallel examples, version 1 and version 2. So let us go through this quickly. I see if we can finish it in 30 minutes or not. So here in this slides, we have pi calculation, we have simple heat equations, 1D wave equation, and array processing here. I don't think we can finish this. So maybe we need to go through the analysis and scalability. 23 slides. Okay. Before we go to this, actually, I will keep this to the tomorrow's class. Okay. But before we go to this, what we need to know is the concept behind parallel computing. Can any one of you guys tell me why we need parallel computing or parallel programming? Why? Anyone, guys?
Hold on. So that we can execute code more efficiently and can see. So when the code is executed efficiently, we can save time and money by sorting big data faster.
So the main key is faster, right? We make it faster. We calculate things faster. So this is the main key. So the main key of using parallel computing is to make things faster, or to accelerate the execution of all systems. So this one speed up, right? Speed up. This is the main key. From your answer, you also said the other word, you said efficiently. So efficiency is another thing actually, another metric that's well used. So here what we need to write is efficiency, ENCY. Okay, so this is the efficiency. And you also said cost, right? Cost. Okay, here we have three things we need to maybe we need to focus on. So the first thing is to make it faster, or to accelerate the speed, which is all about reducing time, right? And this one actually is quite fuzzy. Efficiency can have multiple meanings or different angles of view. So what we need to do is to understand what is the meaning of efficiency. Sorry guys, this one is double F. I make it only one F. So E double F I C I E N C Y. Okay. So here we have the efficiency, as I said, is quite fuzzy. So what we need to do is to understand what's the meaning of efficiency, when the system could be classified as efficient system or efficient program. Okay. Also, what we need to consider is the cost. The cost actually is a very important metric. So when we speed up the processing time, then the cost may reduce, right? So for the main target for the parallel programs is to reduce the time and also to reduce the cost, and to increase the speed, to increase the response, to increase the whatever positive. Okay. So efficiency from here, efficiency is, okay, let me write it. Efficiency in general, okay guys? Efficiency is to, number one, to reduce, oops, to reduce, I don't know what happened. La ilaha illallah. Okay, to reduce any negative thing and the other one is, the other side is to increase any positive things. Okay, so for example here, in order for a system to be efficient, it has to, for example, to reduce the time of execution, and to reduce the, maybe to reduce the cost, or maybe to increase the response time, or maybe to increase the, for example, the battery life, or whatever. Depends on what system actually we are using. Okay, so here in that case, efficiency is to reduce all negative things and to increase all positive things. But in order to do so, we have to have a perfect efficient system. But this perfect efficient system is not easy to achieve. That's why we said any negative thing and any positive thing. Okay, so this is the general meaning of the efficiency in very basic words, guys, for you to understand it as basic as it is. Okay, but inshallah in the next class of tomorrow we are going to go through all of that stuff, so we will understand about the scalability of the parallel system. Then we have to go through the runtime, we have to go to the speed up, we have to go through also the performance metrics, like one of them is the efficiency, by the way. So here we have efficiency, we have, I don't know why slides are white. We have cost here, we have many other things. Okay, so inshallah I see you tomorrow on 11 to take or to cover the performance metrics under the what they call it, performance and scalability of parallel systems. Okay, guys.
Okay, Doctor.
Thank you for attending my class. Please don't forget to record your attendance through
Okay,
podcast.
Doctor.
Okay.
Thank you.
Okay.
Thank you, Doctor.
Okay.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
Doctor.
Okay. Assalamu alaikum wa rahmatullah.